Welcome everybody. Today we're going to be covering three sections, 3.1, 3.2, and 3.3. So we're going to be looking at, start with the complex number system, and then mainly quadratic equations, functions, and some of the applications there. So far we've only been dealing with real numbers, right? Anytime we had an imaginary number, we basically ignored it for now. We kind of just said, oh, it's not real, and we moved on. But in this unit, we're going to introduce the idea of imaginary numbers as well as complex numbers. So we know that the square root of a negative number is not real, right? So for instance, the square root of -1, we know that it is not a real number. And we've talked about this before, particularly when finding domains, right? We always let the inside of that root be at least 0. So now we're going to talk about when that is not the case. So because of this, equations like this, x squared equals -1, would have no solutions. So we do have another number system that we can use to define solutions to these types of equations. And it's called imaginary and also complex numbers. And they're two slightly different things, but they're very similar. So let's start with the idea of defining I here. And I is defined as the square root of -1. So it's not a variable, even though it kind of looks like it, right? Because it's a letter. It is a number. Sorry, Griffin's nose is coming on the page there. And it is the square root of -1. And when you square that, you get just -1 because that square root would cancel out. So for instance, when I square that, what happens is that square root and the square cancel each other out. They're basically opposites, right? So you do get that I squared is in fact -1. So remember that I is not a variable, even though it kind of looks like it. It actually is a number. Now, to write things in terms of I, it does help to kind of break them apart first. So for instance, -7 is the same thing as -1 times 7. So we can take that square root of -1 kind of out by itself. And then this is I. And then here, I can't do anything with root 7, so we just leave it. Now, you can also write it like this, if you prefer. You just want to make sure the I is not under the root. So I is never under the root here. It's always next to it. Here, again, you have the square root of -1 times the square root of 16. This is I, and the square root of 16 here is 4. These are being multiplied, so we typically write this as 4I. Now, we do normally put the I second, although we do sometimes make an exception when we have roots, because it is hard to read the I not being under a root. It's hard to kind of write that. So you can write it either way, but you may see it written backwards instead. And that's perfectly fine. So again, typically you'll see it this way, only because it's a root. Otherwise, we tend to write the I second. Now, we can do a little bit of work here as well. So this negative is just going to hang around for a second. And then this becomes the square root of -1 times the square root of 48. So this piece here, you have a negative and you have an I. And then the square root of 48, you can break down more, right? So 48 is the same thing as 16 times 3. So the square root of 48, we can break down into root 16 times root 3, which is 4 root 3. And then we can put this whole piece together. So what we would have is, you can write it a few different ways. You can write it like this, -4I root 3. That's actually pretty common again, because we usually write the roots at the end. But you could also write it like this, -4 root 3I. They're both correct. Again, you just want to make sure your I is not under the square root. And this is all being multiplied together here. All right, so now a complex number is a number that uses this I, and it's any number of the form a plus bi, where a and b are real numbers. A is typically called the real part, b is typically called the imaginary part of the complex number. Some texts will have the imaginary part be the entire bi, not just b. So there are some differences in definitions here. which is definitely something to watch out for. Now, the complex numbers actually do contain all real numbers and all imaginary numbers. So real numbers are included because when b is 0, then the number just becomes real. The imaginary part disappears. So for instance, you know, the number 2 is the same thing as 2 plus 0i. So it does include real numbers here because that 0 is canceling out the imaginary part, but you can write it in the complex form. If b is not 0, then that complex number is definitely imaginary because you do have an imaginary part left. If you have something like 17i where there's no real part, we sometimes call those pure imaginary numbers because they have no real part. Now, before we keep going, I just want to take a moment and kind of clarify some of this because it can get a little bit tricky for students to kind of understand the breakdown. So what we have here is that at this point, our largest set are the complex numbers. And complex numbers include any numbers that are written as a plus bi. So that includes imaginary numbers. And imaginary numbers could be 2 plus 5i, negative 8 minus 1/2 I, negative 6i, pi I, etc. So these here we tend to call pure imaginary numbers. It's a G there. But notice how they all have an I component there. So if there's an I component, then that complex number is imaginary as well. And it also includes real numbers, right? Because like we said, you could do real numbers because we could put a 0 next to the I. So if we have a 0 next to the I, those are considered real numbers. And again, it works for positives, it works for negatives, it works for fractions and decimals. I won't do every single one here, but it works for all of them. And keep in mind too that, you know, we often break things down into multiple categories, so this is not new. The real numbers, for instance, we can break down into those that are rational and those that are irrational. So things like pi or √2, etc. So your irrational numbers are your decimals that don't end or repeat. With your rationals, you have your fractions, you have your decimals that end or repeat. You also have your integers. We have our whole numbers. And then we have our natural or counting numbers. So remember, your whole numbers start at 0. Your natural numbers start at 1. And then, of course, your integers bring in those positives and negatives, and your rationals bring in those fractions as well. So it's pretty common for a number to be part of more than one category. So you don't want to kind of get too weirded out with the fact that a complex number could be imaginary or it could be real. Complex numbers include everything here. We also call them imaginary when they strictly have an I component as well. Real, we call them when they do not have an I component, but I can call this complex and I can also call this complex. So it's just something to be a little bit careful of, is that most numbers can be defined in more than one way. And you know, the number 1 is perfect. 1 is a natural number. It's also a whole number. It's also an integer. It's also rational. It's also real. It's also complex. So we can break numbers down into multiple categories. I do want to warn you, if you are a Googler in this section, there tend to be a lot of similar but different definitions for imaginary and complex, and even real. Sometimes it gets a little bit weird. So I recommend that you do not Google and you use the definitions in your text. So the definitions that are here are pretty well accepted by the mathematical community. Again, there's some variations. So if you start Googling around, you may find different things. And I highly recommend you don't do that for this section, and really rely on your book for the definitions that you should be using here, because they are correct. Now, how do you add or subtract complex numbers? And they're actually very straightforward. You think of it like a variable where you combine your like terms. So here, the parentheses don't really do anything. They're just showing you the two different numbers that we have. And then what you do is you put your real parts together and you put your imaginary parts together. And just like with the variable, when you add, you just add the numbers. 6 plus 2 is 8, and you keep the I like you would keep the X. When you have subtraction, you still have to distribute through. And then again, I just combine what goes together. So 4 minus 6 is -2. 5i and 3i go together. That would be 8, and then keep the I. Now, I do want to clarify here that when we write complex numbers, we do put the real part first, and then we put the imaginary part second. And that's actually pretty important. A lot of times the homework will mark you incorrect if you put it in the wrong order. It's kind of like the idea of simplifying fractions, right? It's not wrong if it's in a different order, but like with fractions, if they're not simplified, we don't really like them. So you do want to make sure you have the real part first and the imaginary part second when entering your answers. All right, so for multiplication here, you do want to be careful. And this actually relates to this note down here. So when you're multiplying with roots and you see negatives under the root, you want to change to the imaginary form first using the I. So for instance, right, this is the same thing as -1 times 16. And then this one is -1 times 25. So this becomes root 16 is 4, and this is I. And this becomes 5 and I. So we want to change those over first, and then we're going to do any operation. So here, 4 times 5 is 20. I times I is I squared. It multiplies just as you would expect. And then don't forget, and this is the kind of a new part to remember, is that I squared is -1. So you do need to remember to plug that in to finish the problem. Now, if you forget to change to the imaginary form first, and you multiply, what happens is you end up losing that negative, and you lose your that negative in the final answer. So you want to be careful. This is not correct. You want to make sure you always switch to the I form first before you perform any operations with imaginary roots like this. If you already have the I form, then just kind of do what you're used to. So here you could FOIL this out or think of it as distributing. 1 times 1 is 1. 1 times 3i, well, 1 times 3 is 3, so this is just 3i. On the inside, 2 times 1 is 2, so this is 2i. And then the last case, 2 times 3 is 6, and I times I is I squared. So we're just multiplying out as usual. We can combine like terms here, so we have 5i, and then don't forget I squared is -1. So I end up with a -6 here, and 1 minus 6 is -5. So we have a little bit of extra combining to do and simplifying, but otherwise it works the same way. Here as well, I can distribute in. 2 times 7 is 14, so 14i, minus 2 times 8 is 16, and then I squared. Again, don't forget the I squared is a -1, so those two negatives will cancel, and just make sure you write it in the correct order with the imaginary part first. Now this last one is a little bit more like a puzzle. And there are different ways to solve this. So if you have another strategy that you like better, you can feel free to use it. The one I like to do for myself is I know I squared, right? So I know I squared is -1. So if I could get this in an I squared form, that would make me really happy. So I would like to write this as I squared instead. But I can't just make a 58 a square. But you can think about your power rules here. If you do 58 and you divide it by 2, you do get 29. So what I can do is I can rewrite this as I squared to the 29th power, because our exponent rules say that we can multiply when we have a double exponent. So I haven't changed anything here. I've just rewritten this. Now I squared we know is -1, and we can all do -1 to the 29th power. So just think of it, if you have 29 negatives, they cancel in pairs. So 28 will cancel, but there'd be 1 left over. So your answer here is -1. Let me do another one here. So this one's a little bit harder because you know, if I try to divide it by 2, it doesn't come out evenly here. So if I can divide it by 2 evenly, this is a perfect trick to use. If it doesn't divide evenly, what I can do is I can basically just take one of the i's out. So I can rewrite this as I to the 74 times I. I haven't changed the problem. I still have 75 i's here, but now I can divide this 74 by 2, and I can get 37. So I can rewrite this as I squared to the 37 times I. I squared is -1. And again, 37 of them are going to be negative still. So you have -1 times I, which is just -I here. And this is a good strategy to use. So if your value is even, then you can just divide it by 2 and keep going. And if your value is odd, I recommend taking one of the i's out and then continue with the same process. Now, the interesting thing here is that when you solve problems of this style of just I to some power, there are only 4 answers you can get. You can either get -1 or +1, depending on what the power is, or you can get -I or +I, again, depending on the power. So these will all have very similar answers. The conjugate of a complex number is when we change that sign in the middle, and it's very similar to what we did with roots as well when we were trying to rationalize that denominator. So when we're dividing, we're actually not dividing, we're actually going to use conjugates here. So for instance, if I divide 2 minus 5i by 1 minus 6i, I'm not going to actually divide anything. What I'm going to do is I'm going to multiply by the conjugate, supposed to be a u there, get of the denominator. And all that changes is you just change the sign in the middle. So for instance, I'm going to multiply this by 1 plus 6i over 1 plus 6i. And I'm just going to go ahead and do some distributing out here. So let's see, I get 2 times 1 is 2, 2 times 6 is 12, so that's 12i. On the inside, -5 times 1 is -5i, and then -5 times 6 is -30, and then I have an I squared. In the denominator, 1 times 1 is 1, 1 times 6 is 6, so 6i, 1 times -6 is -6i, and then here, -6 times 6 is -36, and then I times I is I squared. In the denominator, notice that you do get this canceling in the middle, which is supposed to happen. And then we're going to keep simplifying. So I have 2, and then here I can combine my like terms. So plus 7i minus 30, and I squared is -1. In the denominator, I have 1 minus 36. And again, I squared is -1. So let's go over here. So I have 2 plus 7i. Our 2 negatives there will cancel and give me 30. Here, my 2 negatives will cancel and give me 36. So I have 32 plus 30, 2 plus 30 is 32, plus 7i, all over 37. Now we're basically done, but don't forget we want to write our final answer as a plus bi form. So I actually do have to separate out the fractions here. So I'd write it as 32 over 37, which is a real part, and then 7 over 37 with the I for the imaginary part. If you could simplify your fractions, you would, of course. I can't though, so I'm done. Okay, so now that we know how to deal with imaginary numbers, we're going to do some equation solving. And we're going to do quadratics. And quadratics could have imaginary answers, or they could have real answers. So they could have any combination of them, depending on the example here. So now we know how to work with them. A quadratic equation is any equation that can be written in this form. So your highest power is 2 there. Or your highest exponent is 2. The function is the same. Sorry, this is a typo. There should be a C there, just like this one. So you can also use function notation here. They are functions. And what happens is they're functions when they're shaped like this. So we're not talking about parabolas that go sideways here. We're just going to talk about either your up or down parabolas. When it's written in this form with an equals 0, we do call that standard form, which is helpful in some cases. The zeros of a quadratic function are the solutions of the quadratic equation. So zeros and solutions, again, are used interchangeably. Also, sometimes the word roots as well, which I have here for you. So these, again, are all used interchangeably. They can have real or imaginary solutions. And here's a really nice piece is if the solutions are real, they are also the x-intercepts of the graph, which is really helpful. So there's basically three things that can happen with a quadratic. And again, the shape could be up or down, so I'm not going to do every single possibility, but I'll show you the three kind of main things. One thing that can happen, for instance, is your graph doesn't touch the x-axis at all. So in a case like this, there is no x-intercept on the graph. So what that means is that there are no real solutions, and all solutions are imaginary. So it's actually really helpful to graph some of these to check your work. It's not a perfect check, but it lets you know if you're in the ballpark. So if you have no x-intercepts, then your solutions are there, but they are imaginary. Another thing that could happen, and I'll just do one going the other way this time, is you could touch the x-axis one time. So here you have one x-intercept. So what it means is that there is one real solution. What happens is when you solve, you do always get two answers, but in this case, it'll be the same answer written twice. So we call it a repeated solution. So that does happen occasionally where, you could be solving and you get that x equals 4 and x equals 4 again or something like that. So in that case, since there's only one unique answer, it would only have one intercept. And then, of course, the other thing that could happen is you hit the x-axis twice. So you have two x-intercepts, and that means that you have two real solutions. And they are different, right? So they're not the same. There are two different points. So there are two different solutions. And those x values there of the intercepts correlate to the actual solutions. All right, so graphing is a nice way to start. It's not the best way to solve because sometimes the points are hard to see. If the points are pretty straightforward, then it's a great tool to use to check your work and stuff, but they're not always as clear and they don't work for imaginary values either. So let's look at some solving strategies here. All right, so our first strategy is to solve these by factoring. And this is helpful when factoring is easy and of course it's possible. Not everything is factorable. So there's different strategies we can use to solve quadratics, and factoring is one of them. But it's only good if factoring is actually possible, particularly if it's easy, right? If you're spending all day factoring, then it's not going to be a helpful strategy. And we use what's called the principle of zero products here, or they also can call it the zero product property if you've heard that as well. It's the same thing. And it basically says that if two things multiply to be 0, then one of them has to be 0. So let's just say and. Or at least one of them is 0, right? There's no way to get an answer of 0 if one of them does not have a 0 in it to start with when we're multiplying. So what we do is we start here by setting it equal to 0. So if we're solving using factoring, we want to have equals 0 to start. So we can use this property. So I'm going to subtract that 3 to both sides. And I get 2x squared minus x minus 3 equals 0. And then I'm going to go ahead and factor it. And again, factoring is something you should already be comfortable with. If you need more help there, let me know and I can point you at some resources. The just-in-time section in our text does have factoring as well. And then once you've factored your polynomial, make sure, of course, you factored it correctly. So you do want to, check your work. You're going to set each factor equal to 0 and solve. So at this point, I would take the first factor, 2x minus 3, set it equal to 0. I would do the second factor, and I'm going to solve each of them individually. All right, so here I have two solutions. One is 3/2 and one is -1. And this is the strategy that we can use when we're solving by factoring. Now you can check, let me bring up my calculator here. I'm going to bring up Desmos, and I won't do this for all of them, but I just want to encourage you, to, again, to try to check some of this. So if I put in my equation here, I like to put it in with the equals 0 on one side. I do find that it graphs nicer that way. So I'm going to so on my graph, I'm going to enter this as y equals 2x squared minus x minus 3. When you put it in with the original, sometimes it gets these weird vertical lines in it. So you do want to actually kind of bring everything to one side and use a y there. Or a function notation is fine too. To graph, and you can see here that I do have two x-intercepts. One of them, if I tap it, is there at 1.5, which is this one, right? 3/2 is 1.5, and the other one is at -1. So again, you don't need the zeros there. It's just the x values that you're looking at, and that is a nice way to check if you are on track with your answers. You can see those as the x-intercepts if they are real. If they're not real, then you won't see them on the graph. The graph would either be above or below the x-axis instead. All right, another strategy is called the square, or using the square root property or the principle of square roots. Again, they're really the same thing there. This is helpful when all variables are in a square or are being squared. So for instance, take a look at this example here. I have an x squared, but I don't have an extra x hanging around like I did up here. All my variables are being squared. So this is when this property is the most helpful. And what you do is you actually solve and get the x squared by itself. So I'm going to bring the 10 to the other side. I'm going to divide by 2. So it's like regular solving, but you're going to be left with an x squared in the end. And then what you do here, and this is this property right here, is that you take the positive and negative square root of both sides. That negative is on the outside, not the inside. So I take the square root, but always the positive and negative. So you're getting two answers there. You're getting that x is equal to positive root 5 and x is oops. I think we're okay now. I want to show you another example here as well. So this one looks a little bit different, and you may be saying, hey, but that's just an x. But it's actually a square, right? Because see how the x is inside a square, right? The whole thing is being squared there. So we can apply this property as well. So you get the square by itself, which we did. So there's nothing left with the square on this side. And then you take the square root of both sides. Again, don't forget that plus and minus. So on the left, you're left with x minus 3. On the right, you have plus and minus the square root of 9. Now, here you actually can simplify, right? The square root of 9 is just 3. And now I have two different problems. I have x minus 3 equals positive 3, and x minus 3 equals negative 3. I solve each of those little equations, and I get 6. And I get 0 as my two solutions. So this can be applied as well in other cases that may be not as straightforward. But here our x is still being squared and there's no other x's hanging around, so I can go ahead and take that square root of both sides. So it's a nice strategy, and it's pretty quick when you have that combination here. So option 3 is to use completing the square. This is good when the first two properties or strategies don't work. This always works. So you may be asking, well, why don't I just use it all the time? And honestly, it's pretty tedious to do. So that's why we don't use it all the time. Your first two strategies tend to be faster. So for me personally, when I'm solving a quadratic, I will usually check to see if I can factor it first, or I'll check to see if I could use that square root property, if there's no extra x's hanging around. Those are usually my go-tos. If that doesn't work, then I'm going to move on, and I can do completing the square, but it's a lot more tedious. Completing the square is actually also helpful with a lot of circles as well. So if you're continuing on particularly, this does come up occasionally when solving and working with circles. So it does have other applications. All right, so my problem is on the next page. I'm going to kind of walk through it, hopefully with the steps at the same time here. So how do you solve using completing the square? So first thing is you're going to isolate the terms with variables on one side and terms without variables on the other side. So very different setup here. You want all x's on one side and all numbers on the other. So I'm going to bring the 3x over here and bring that 1 on this side. To bring it over, remember we would do the opposite. So subtract the 3x. Here you would be adding the 1. So I'm going to set up as 2x squared minus 3x is equal to 1. And I'm going to fix my numbering here because these are a little off. This should be 5. My second step is going to be divide by a if a is not 1. So by a, they mean the leading number with the x squared. So the number with x squared. So I'm going to divide everything by 2 here. And I have x squared minus 3/2 x is equal to 1/2. Now, when there's no fractions, it's actually not too bad to do. When there are fractions, it's a little bit harder, but we can still deal with it. All right, our third step here, and this is very prescriptive, is to calculate half of b and then square it and add this to both sides of the equation. So when they're talking about b here, they don't mean the original b in the problem. They mean at this step. So this here is your b. And it includes the sign as well. So our b is negative 3/2. So what I'm going to do is I take 1/2 of b. So that's 1/2 of negative 3/2. You're just multiplying those there, which gives me negative 3/4. Okay. And then you also square it. So once I have that, I'm going to go ahead and take that and square it. Negative 3 squared is 9 and 4 squared is 16. And then I'm going to go ahead and add to both sides of the equation. All right, so I'm going to have you guys just kind of refer back to the steps over here. I'm running out of room and I want to make sure you can see all of this. So I'm going to kind of finish step 3 here. So I take my equation, that x squared minus 3/2 x, and what I'm doing is I'm adding that 9/16 to both sides. Now what happens is, so this is very prescriptive for a reason, because when we do it like this, the left side will always factor as x plus 1/2 b squared. So like this. So here, my left side is going to factor as x, and then our half b was negative 3/4. So minus 3/4 squared. And then on the right side, you do have a little bit of work to do. So 1/2 plus 9/16. The first fraction I can multiply by 8/8. So I have 8/16 plus 9/16 is 17/16. So I do a little bit of cleaning up there. All right, and then the last step, the reason why we did all this is to now use that square root property that we just learned about, because all your x's are now in a square. So we can go ahead and take the square root of both sides. Don't forget plus or minus. This is step 5. So on the left, you have x minus 3/4. That square part goes away. Here you have plus or minus. Now, I can't do anything with root 17, but the square root of 16 is 4. So I can at least simplify part of it. And then I have a little bit of work to clean up. So I have x minus 3/4 equals root 17/4. And I also have x minus 3/4 is equal to negative root 17/4. I add 3/4 to both sides. And finally, I get x is equal to 3/4 plus root 17/4. Or over here, x is equal to 3/4 minus root 17/4. You can also combine these if you want to. So you could write it as 3 plus root 17 all over 4 and 3 minus root 17 all over 4 because they have the same denominator. So these are our two solutions in this particular case. Now, these are real numbers. I know they look really weird, but there's no imaginary numbers here. The roots are positive, right? So they are real numbers. So they're just decimals. So that's something to keep in mind. If you go to check on the graph, it's not going to be a perfect check because you're looking at decimal answers, but you can still do a quick check to see if you're on track with those two x-intercepts. Now, the fourth strategy is the quadratic formula, and this one always works as well. And it tends to be a lot faster than completing the square. So this tends to be a favorite of students because it does work. And what happens is it gives you a formula to plug into to solve for x. It is derived from the strategy that we just saw. So if you're interested in looking more about that, you can, but we're not going to worry about the derivation. I'm just going to show you how to use it. So you do have to start with an equals 0 here. So I'm going to bring the 7 to the other side, and we do that by subtraction. And then what happens is, make sure your powers are in order. So this first value is going to be 3, the second would be b, and then the last one would be c. Just watch out for your negatives. And then you literally plug those values into the formula here. The hardest part is that there's a lot of negatives. It's really easy to make a small mistake here, very, very easy. So you just want to be careful with the arithmetic. So there's a negative on the b, so our b is 2. Here I have b again, so 2 squared minus 4. And then a is 3 and c is negative 7. And then a is 3. And you want to make sure that fraction bar goes across the whole thing. So it's negative 2 plus or minus, and I just start to clean it up. 2 squared is 4. Here, let's see, I have the two negatives will cancel. 4 times 3 is 12, times 7 is 84. I have a 6 on the bottom. Four and 84 is 88. And then I'm just going to do a little bit more simplifying. So, square root of 88. I can definitely take a 4 out of that. And that leaves me with root 22. And root 22 I can't break down anymore. So I can at least do some of this, 2 root 22. So my answer becomes negative 2 plus or minus 2 root 22 all over 6. And I do want to clean this up a little bit. So I'm going to go ahead and split this now. Here, I can take a 2 out of each of these. I'm left with 1/3. And same thing here. When you're simplifying the fraction, don't go inside the root. So I have my answer, x equals 1/3, sorry, negative 1/3, plus or minus root 22 over 3. I don't need the extra 1 because 1 times root 22 is just root 22. But again, here are my two answers. If you want to write them separately, you can. One has the plus, one has the minus. You can also put them back together. So you can do negative 1 plus root 22 all over 3 because it's the same denominator. This is also correct. These are real numbers. We actually haven't seen any imaginary problems yet because the inside of the root is positive. So if the inside of the root was negative, then you would simplify that and use the I form instead. But these are both real numbers here. The part of the formula, the b squared minus 4ac, is also called the discriminant. And basically, that's what decides how many solutions you have, the inside of the root. When it's equal to 0, there's only one real number solution. So again, you get that 1 x-intercept. When it's positive, so if it's greater than 0, like we saw here, you have two real number solutions, right? The inside there was 88, which was positive, so you had two solutions. And if the inside of the root is negative, then you have imaginary solutions. They actually happen to be complex conjugates of each other. They are both imaginary. So those are the different things that can happen with the solutions. Quadratics can be pretty tricky until you get used to them because there's so many different ways to solve and you don't know which one's going to work. So when you get a question, for me, I like to try factoring first or the square root property. Those tend to be faster. So if you are pretty comfortable with your factoring or if you can recognize when to use that square root property pretty easily, then you can jump into one of these two steps. If you find that they're not working, right, so you're not getting anywhere with them, then for me, my other favorite is definitely the quadratic formula. But you can use any strategy that works. So most quadratics have more than one way to solve. For instance, the quadratic formula and completing the square always work. So every quadratic has at least two ways right there, but some of them will have more if they're factorable or if they can be used with the square root property. So whatever strategy works is fine, and it takes a little bit of time to kind of play around with the different quadratics is your best option. But you should find one that works. All right, I want to do two examples here that kind of look like quadratics, but they're not quite there. So we use something called substitution to make them reducible to quadratic form. So basically, we kind of make them look like quadratics. So if you look at this one, it's pretty similar to what we've done, but instead of having a square and a regular x here, I have a 4 and a 2, right? The powers are off, but otherwise it looks pretty similar. So what I'm going to do is use substitution. And we do it in a very specific way. So first of all, it should be in order, from, descending powers, decreasing powers. And then what we do is we let the u, we use u for substitution, so you can see the letter u there, be that middle term variable. And you also want to see if u is equal to x squared, well, u squared would be x squared squared, which is x to the 4th, right? Because 2 times 2 is 4. So you should be noticing that this piece here is u, and then this one should match with u squared. But the middle term is where you start. That's how you figure out what to substitute. So u is how we substitute. And then when you square it, you should get the leading piece. So that's how you can check that this actually is going to work. If for some reason, your leading term here was x cubed, x cubed instead, then this is not a good strategy. So both pieces have to match. And then what you do is you change it over. So I'm going to rewrite it. Instead of x to the 4th, I'm going to write it as u squared. And instead of minus 5x squared, I'm going to write it as minus 5u. And everything else is going to stay the same. And now it looks like a regular quadratic. So now you can use any strategy that you find works. This one is factorable. minus 1 minus, oops, 4, almost wrote a 5 there. So it does factor as u minus 1, u minus 4, and then I can use my factoring strategy here, set each factor equal to 0, and solve. So I have u equals 1, and I have u equals 4. Now the only thing is we're not quite done because our answers were not really used. They were x's to start with. So what you do is you take your two answers and you substitute back in. So our u was x squared. And then you often have a little bit extra solving here. So for x squared, we can solve that by taking the square root of both sides. And we have that x is equal to plus or minus the square root of 1, and x is equal to plus or minus the square root of 4. Now the square root of 1 is just 1, so I have plus or minus 1, and the square root of 4 is 2. So I actually have 4 answers here. X could be -1 or +1, -2 or +2. So if you graph this original equation, you would actually see 4 x-intercepts. And it's different because I don't have a square power here. My highest power is 4. Your highest power can actually tell you up to how many different answers you can have. So it does make sense here that we have additional solutions. For this one too, again, it looks pretty similar, but instead of just having a 2 and a 1, we have this division by 3 here. So again, it's almost like a quadratic, but it's a little bit off. So you start with the middle. That's always going to be your u. So u is going to be t to the 1/3, and it's just the variable part. It's not the number. And if you square it, well, 2 times 1/3 is 2/3, right? So you do get t to the 2/3 here, which matches. So this is u squared, and you see that both parts match. So we're going to rewrite u squared minus 2u minus 3 equals 0. This one happens to also be solvable by factoring. They're not all, but a lot of them are. At least in the textbook, I should say, a lot of them are. In the real world, a lot of polynomials are not factorable. We set each piece equal to 0. But for this solving part, you can use whatever strategy works. If you like the quadratic formula, you could use quadratic formula here too. And then just don't forget that once you have your answers, you do need to substitute back in. All right, so t to the 1/3 equals -1, and t to the 1/3 equals 3. Now, I don't want to have a t 1/3. I want just a t. I would like to have an answer. So think about how can you cancel out a 1/3? I can multiply it by 3, right? If I raise it to the 3 power, 1/3 times 3 is 3 over 3, which is just 1. It cancels it out. So I'm going to raise them to the 3rd power. -1 to the 3rd power is -1. Same thing here. 3rd power is 27 though, 3 times 3 times 3. So I have 2 answers, -1 and 27. Now, there are a lot of other examples in your text. Again, I don't have time to do all of them in an hour lecture, and I always tend to run long as it is. So do see your text for some application examples here as well. All right, there's one more thing I want to show you guys, and that is about graphing, which is really important. Now, I know we have Desmos to graph, but we do need to know how to graph by hand as well and to look for key features. So quadratic functions can be written in different ways. The one we've seen most often is like this, right? And I'll come back to this, where you just have an x squared, an x term, and a number. But sometimes we write it like this. And this is called vertex form when it's written like this. And actually, the reason why we use the word vertex is because when we graph our quadratics, they're either going to look like this, they're going to face upward, or they're going to face downward as a U. And this lowest point here is called the vertex, or in this case, it's your highest point. It's called the vertex, that center point. We label it as H, K. So when you have a U shape facing up, it is your minimum value. When you have the U shape facing down, it is the maximum value. you do have perfect symmetry here along the line x equals h, so whatever that, that value is. I know my drawing's not perfect, but you would have a nice mirror image there. And how do you know if it goes up or down? That's actually pretty easy to figure out. If your a value here, if your leading a value, whether it's in this form or even in this form, it doesn't matter. When your a value is positive, it goes up. And when your a value is negative, it goes down. So just by seeing the leading piece here, you can know a lot about your function already. The nice thing when you're in vertex form is you actually can pick out the vertex right away. So that's why they call it vertex form, because you don't have to find the vertex, it's already given to you. You can kind of just see it. It's kind of like the idea of slope, right? Sometimes we can just see the slope in an equation. And that's what this is here. So here's an example. Let's kind of go through how to use it. I'm just going to rewrite it because it's split onto two different parts. And then I'm going to match it up with the general form that's up here, right? That kind of base form. So here I can see the a is out front. So my a is 3, which means that is positive, right? So my graph is definitely going to be something like this. It's going to be an upward U shape. Now I have my h matches with the 1/4. Notice that I have a minus minus here. So the signs don't matter. The signs are the same. I'm just looking at the number. H is 1/4 here. And for the last part, I do have the k. Now you do want to be careful because the signs are opposite, right? So k is not going to be just 2. It's actually going to be negative 2. So you just want to watch the signs here. If you don't have the same sign, you need to think about that. So here, it's supposed to be a plus k. I have a minus 2, so it actually is a negative 2 for my k value. If my signs here were different, right, like if this was a plus 1/4, then it would actually be a negative 1/4 in my answer here. So we have to watch out for those signs like we've seen before. So our vertex is at 1/4 negative 2. And that means that the axis of symmetry is at x equals 1/4 as well. So I'm just going to do a super rough graph here. So we have -1, -2, and this is going to be 1. So our vertex is at 1/4 -2, so about right here. I'm just going to estimate that. I know it's going upward, right? So it's going something like this. I don't know where it crosses the x-axis. I don't have those points yet, but it's going, it's going to keep going up. I just don't know where it's going to cross. And then you have that axis of symmetry right here. Making sure that you have a nice mirror image on both sides. This is your vertex at 1/4 -2. So here, your minimum value is -2, right? That's your lowest value. There is no max. It does keep going up forever. I could also find extra points, right? So if I wanted to, I'm not going to, but if I wanted to, I could make a table and I could plug in different x values. Maybe I want to plug in x is 0 or 1 or -1 and just see what happens. So you can always find extra points, but that vertex is sort of the most important point because it gives you that center. Now, what do you do when you don't have the vertex form? So there's different things you can do here. One is to use completing the square, and you can actually put it in vertex form. So I recommend you look at your text or other resources if you're interested in that. The easier way, I think, though, is to use this formula here. So we can find the vertex by using this formula, and it gives us the x value. Let me just write it out a little bit clearer. It's -b over 2a. So both the 2 and the a are in the denominator there. All right, so here we have our equation. Again, it's not in that vertex form. That's already kind of pre-factored. So we have to find the vertex a little bit more manually. So I use the formula -b over 2a. Now here, my a value is -1. My b value is 14. So we're in order, power, and then the a value is first and the b value is second. So this becomes -14 over 2 times -1, Negative 14 over negative 2 is positive 7. So this is your h, right? That's the x value. And then what you do is you plug it back in. So now you find f of 7. So whatever you get here, you plug in. So I go to my equation and I plug in 7. Now be careful, that negative is out front. So 7 squared is just 49. 14 times 7 is 98. And you actually end up with 2. So this is your k value. So the vertex is always of the form hk is going to be 7, 2 here. Determine whether there's a max or min value and find that value. So max or min for quadratics, you want to think about the vertex. Now here, notice how my a value is negative 1, right? It's less than 0. So my a is less than 0. My graph is going to be like this. And we already found the vertex is right here. It's 7, 2. So in this case, our vertex is a max, right? It's at the top of the graph. So here we have a maximum, not a minimum. And our maximum value is going to be 2. And remember, when they're talking about value, they typically want the y value there. So the highest point of the graph, the y value is going to be 2 in this case. So when I have questions about max or min, you want to think about, okay, is the graph going up or down? And you need to use that vertex. So many times a question will not refer to the vertex. They'll just ask you max or min, and you kind of need to know that. So what is the range? Remember, your range are your y values. So think about the graph here. The highest point, right, was 2, and then it keeps going down forever. So your y values are less than or equal to 2, or negative infinity to 2. So it's a positive 2 there. We do use a bracket because you do have equality here. It does touch that value. And then finally, on which interval is it increasing or decreasing? Again, I'm just going to draw that picture one more time down here. Right, here's our vertex at 7, 2. And again, you have that axis of symmetry, right, at x equals 7 that perfectly splits the graph. So we read a graph from left to right. So the graph is going upward on the left. So this part is increasing. And then it goes downward on the right. So this part is decreasing. So we are increasing from negative infinity up until 7. And then we are decreasing from 7 to positive infinity. Remember that when we're talking about increasing or decreasing, we always refer to the x values for increasing or decreasing, and we always use parentheses there. That kind of takes us back a couple lessons. So you want to just be really careful that you're using the right notation in all these cases. Again, you want to see your text for more applications. There are a ton of applications on quadratics. Quadratics are wonderful. There's so many applications, including a lot of like falling object applications and things like that. So check out your text for some examples there. But again, keep in mind those keywords of max or min with quadratics typically means the vertex. So you're using that vertex point, and then you just need to know which way the graph is facing.